Let me show you what a shear failure looks like in this design. Not number 12 and not number 11. It's the deck. It's the dead loads. So what do you have here? Different elevations. This would be indicating of shear going on. One is staying still, stationary, and the other one's bypassing, going the other direction. And for orientation, let me grab you some photographs of shots. So this part that we're looking at, this is this section right here, is this section right here. There's the 12 column. There's my burn marks or whatever I'm referring to them as. There's the top part. It is not going down in elevation. It is not going down. And why can it not go down is because, let's grab the drawing. It's sitting on top of a pier here. This is all solid. This cannot shear. This can buckle, but it can't shear. Oh, it can have a lateral shear like that, but it can't. It's not shearing in that capacity. Here's number 11, here's number 12. So if you guys can visualize the load of this deck, the weight of this deck, trying to transfer all this load out to the pier is what it amounts to, and then down to the earth. It can't make it down 11. If it made down 11, we would see, we wouldn't be where we are. Those photographs wouldn't indicate that way. This isn't, I showed you the other video where this is not shearing off or pushing off number 12. But now we're at the previous video to this one. So if you want to find it and you've just came here with this video, then just look at the previous video to this one and you'll find it on this channel. I have two channels. So this is shearing going on over here. The dead load of the bridge is deflecting in the middle, deflecting between the spans. Let's get the photograph here. I'll go to the top. I need to get to the top of this one. And hopefully I'll run across a pier when I do it, or it's in the top image. All right, I'm just going to race to the top. Bear with me. Sorry about the screen. All right, scroll down. It's going to be pretty quick, a rendering, a quick drawing right here. So this is the span we're talking about. This is number 11. 2016 stamped. There's a pier right here. The loads transfer down. But the unsupported span is from the edge of this. It's where the first point of contact is to the first point of contact over here. That's the unsupported span. These are not in place, so I will not call these supports. And they wouldn't be supports anyway. So the unsupported span is from here to here. Let me think about that on the post-tensioning. That's the unsupported span. Okay, so the dead load of the entire bridge has to make its way from unsupported span to unsupported span. Deflection, typically the deflection will be in the center of this bridge, typically. We got post-tensioning, so I don't want to confuse you guys with how post-tensioning redirects. But the deflection would be typically in the middle. So imagine if they did have some, if the report show, the surveyor reports show deflection, and they showed the deflection when it was an as-built, after they removed the form work, and they took surveying, showed the deflection in the middle of, say, a 1/4 inch. It's moving, it's creeping. It's creeping. I don't know what they would consider acceptable deflection, on this. Once you remove the form work, I would think that no deflection would be too typical for this. That you wouldn't want deflection on this span. It would just show the direction of the loads, and you don't want you wouldn't want to see it. If anything, I would think a bit of a camber. But remember, this is also a handicap, so they have to have a 1/4 inch slope on this guy also. No more than a 1/4 inch slope. Now so the loads are, I say they made it over to number 10. And why do I say that? Because we see the break here. We don't see the break here in the middle. So I'm saying this design probably was working pretty darn good. They just didn't implement it. That it probably would have worked. I know that's not what you guys want to hear, because quite a few people ask me, it's junk, it was wrong, it couldn't have worked. Well, I say that I may hate that it failed, and it goes against some thinking. But if we just take the data, I say this design could have worked. That they implemented the CEI should have been on top of this. I'm blaming the CEI now. Should have been on top of this and not allowed the removal of the formwork. It should have had more testing in the impound, I call it, off the side of the road. Everything should have been addressed 199% over there. And I do mean 199. I mean, when you thought you were 100%, go again. Go at it again. Doubt yourself. Get more people to doubt you. Really go at this thing and load test this thing on the side of the road. They didn't load test it. They could have load tested it over there when it was on the span to span. They could have put some water baffles up here, loaded it with water, just a little bit, but they didn't because why? It was incomplete. So don't put an incomplete structure over the road if you don't want to test it for the amount of rain that might have been on it over there, the amount of wind that might have happened that caused this. It should have been tested over there, but let's move on. Reason why I state that the structure could have worked was because we see the breaks here, approximately here and here, which means the loads failed. The bridge failed here and here. It didn't fail in the middle. So I would say that this deflection was probably not happening in the middle. This thing was doing pretty darn good. In fact, Denny Pate, I don't know what his PowerPoint is all about. And with all my 1 year of going crazy over this structure, I wouldn't see why you'd want to post-tension this anymore at the day of the as part of your structural repairs. But with the knowledge that I know that how it failed, he didn't have that knowledge, right? It didn't fail yet. But if he used a surveying, he would have determined the low point of this structure. And if the surveyor would have determined this, they would have discovered that it's, you see the bricks, right? So you see the bricks, you would clearly say it's moving right there. Then you use your engineering knowledge and go, wow, this looks like a shear failure under dead loads. So here's the cracks here. And here's how they present. You would say, wow, this bridge is creeping down. And I don't mean creeping anymore. It's hunching down. It's going. It's got movement. It's beyond creeping. It's breaking, and it's sheer failing at this point. This is clearly a failure. This is not some little nothing. This is a failure. And now you talk about the failure and how did we get there to the failure? And there were multiple engineers, the CEI, Denny Pate, MCM, structures, all these people I'm sure have knowledge of shear failure, of what it looks like in real life. So we come to right. This one is an odd one. I wouldn't necessarily call this shear failure. It's on the backside. It's here. I would call this like a compressive, failure going on. But also, and here's a crack here. This crack is not and if you guys remember, it's not a compressive crack. It's an opening crack. So already the bridge is hunching down, and as it hunches down, breaking away, these forces are creating these breaks. And this is a separation. And if I can only see on the back side of here, we might be able to see some compressive fractures going on in the concrete. And they look like they're blowing out at that point. They look crumbling, contact-ish. And that would be more like this. I need a closer shot for you. Never mind. They would look like that. See, it's broken debris. This didn't break in pieces going chip, 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 chip. This had some compressive forces at a moment, and it crumbled. It broke these pieces up that way. And then it had a reversal, and the reversal went the other direction. So first we had a compressive impact here, force, and then a reversal. Compress, reversal. So it had two actions going on there. And you guys know that I'm crazy over looking at things of microscopically breaking things, and then concrete and things like that to see what's going on at each impact, and I evaluate. And so this is that impact. All right, this is what's going on force-wise. Now this one is a shear failure of the deck. And again, a survey would tell it at that point before proceeding. So CEI was wrong to allow this procedure to continue, the tensioning. But I think I'll give you the intent of the tensioning in a minute. Let's go. Yes, I'm trying to find. So we know it broke here and here. So that's where the forces, the load, dead load resolved itself. That's where it was the greatest forces on this, as you saw those cracks a moment ago. Gosh, I need to put those two together. So as you saw, I just did tab-wise. As you saw this, that's the shear failure of the loads resolving themselves right at the end of that structure. Now I have this one. I wanted to come to this one. This is the second time I made this video, and this will be the final one. It could also be that this thing is winging, that the the transverse post-tension cables that they have in here, the transverse cables, are winging, are failing, and this thing is like winging down, and well, more on this side perhaps, winging downwards. Could also give you this guy going over there, that it's not enough to put the loads back into the center, and you get this weird thing going on. I would love to see more of this photograph, because look, it looks like it might be wrapping around and coming around to the other side, but you know the way the NTSB is holding back on the photographs and giving these cropped images, because this is just junk. I don't think the guy came down here and photographed this and we're looking at a cropped image. Because if you come in close and photograph like this, these numbers would be a lot more clear. But if you crop photography, they get blurry like that. They get pixelated. And so I think we have more to this image than meets our eye at this point. So here's the cracks that we're looking at, roughly right about here, coming over, wrapping around this guy and coming this way. So now let's talk about that crack we see in the photographs. Let's tie it in with the NTSB crack. So I'm looking at tabs, guys. Sorry. I'm going to tie it in with the same hunching down. Okay. This is the NTSB. And the hunching down, the separation of the canopy, hunching down, this crack being in line with what's going on. The deck crumble. Yeah, I'm sorry, I'm talking too plain now. The deck, I'm trying to show direction. Hold on. Okay. Okay, I'll move images. The deck coming, but we know now through hindsight, I'm going here. Otherwise, if I didn't have the video, I would still say it's here. That is pulling down, and I would have said that it's from there to the center line, because that's where they usually resolve themselves under just dead load, if this is all symmetrical in weight. So I would, wherever it's symmetrical in weight, and then maybe I would have even said that, because that would have been a tension break in there, I would have probably put it somewhere, in theory, without the video, I probably would have said somewhere here and here. I would probably said, talking to you guys, saying that it's probably leaning down here, and putting this stress, resolving its break in a deck here, as we see in the photographs, in here. But now I have a video. I don't have to worry about hindsight. I know that the loads are here and here, and all this weight has made it to this point. Oh, can I get some moisture here, please? It's lunchtime, guys. So all the weight is resolving its load, transferring here and right about here. And that's where we get our shear moment. So the deck is pushing down here. So the stresses would be at this point and this point. And as it pushes down, and we got some movement. To get 2 inches there, I don't know what drop we have here, but we got a significant drop. That would then put tension in this number 11 also, cracking it. Now let's talk about then Denny Pate coming along going, hey, I just need to put this thing back. I need to straighten it back up. So how would I do that? What if I post tension? If I added more tension into this would put a reversal in this falling down by redirecting it back into, as an anchor here, redirecting it back as you would think of a bridge. This would become the anchor, the abutments, and I just redirect and cranking it back up, and this will then lift the bridge back into alignment craziness, because you would just think it would fail once you try to bring those many forces back over there. One way or another, you wouldn't think it would do it. Maybe the rods would be able to take it, but the concrete, you would say, come on, it can't take it. All right, I'm going to terminate the video, but I just want to show that. I'll summate. Oh, I forgot, guys. A couple people want me to do summations. So summarizing again, there's your opening. That's your shear failure of the dead load of the deck weight resolving itself. Yep, not good enough detail. Hold on, I got to scroll down a little bit to show you. Resolving itself above the pier and down the... I can do even better than that. I can find one more photograph. And this is that summation thing someone asked me to do, so bear with me. I'm looking for the abutment. I mean the pier connection. La 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 la. Okay, we're getting there. Bear with me. It's right past these guys. It never seems like it's that far away when I go to search for it. This probably gets me every time out. I always think I'm just going to move my finger a little bit and be there. Right here is where the pier is going to land. Again, this is the failure lever right there. And that would explain why this hunching down here and here. Again, I would have thought it was the middle without the video. Hunching down, and you get your separation cracks. That the top of that post tension would have kept the top part of that in place. Well, because of the way it's post tension. So it keeps the top in place to allow the separation. Aha! The shearing of number 11 in half. Can I reach that far? I think I could. I could probably reach that far and call it the shearing of number 11 internally. Creating that longitudinal crack. When I say longitudinal, directional crack. But also it could be the compression of number 11. But I'm liking this instead. And now, come on. Thought this had a pier cap down here. Come on. Guess not. All right. So, right there. Right there. If we could see the other side of this should be compressive on the other side if it's a lateral shift to the left. The rotation to the left, that means towards us. Camera angle. Camera towards us. So, and on this one, sorry, I got to get a meeting on you guys. Sorry, this should be camera left. So deck rotation to the left. Shearing downward, the dead load from between where we know it collapsed, where it failed, where I'm saying it failed, which is here and here. As this whole entire section of bridge lowers itself, it was a bend in the cables up here, obviously trying to hold on, putting force back here. There's what, 4 cables there and the rest of them here. As this creeps down, this creates so much force elongation in the cabling and the deck cabling that it initially, that force initially is the first impact of this, with this on the other, with the solid surface behind it, rebar between it perhaps. There's your first break. It's relieved, and then it opens up. And so there's your stress relief here. And the reason, well, they're only showing this, right? So there, it goes off to that direction. The reason why I'm saying it's not that it's a torsion, a torque, if you will, a left or right action going on as we, oh, great. As we look at the bridge, yeah, good. As I'm saying it leaned more to the right now. Before it leaned to the left. It wasn't symmetrical in its downward hunch, if you will. That it was first to the right. It was first to the right, more to the right, and down. So it had a twisting action going on here. It'd be nice to see if on a pedestal, if it lifted up just a touch, off it lifted up, or did it just hold steady and it just torqued down, hunch down, twist down, right here. Terminating the video. I know that was confusing. I see it in my mind and I try to talk to you guys about it, and it can get quite twisted sometimes. Trying to share what you visualize into words, but that's what I visualize. Down to the left as we're standing on the bridge. Down to the left, also down in the center. I mean, down at the, not the center. I would have normally thought center. Down at the, great. You show between the top of the canopy and the lower part of the deck. Between number 12 and number 10 and 9 interconnect node, and the top node and the number 11. So I see the rotation happening there. Hunching down. There's our shear. Resolving on this side. Everything's equilibrium for me, remember? So it resolved on this side more so for weight, whatever reason. It didn't do it by mistake. It created its equilibrium. These cracks are in equilibrium. They are in equilibrium. So you're looking at, you know, however the design came out, this is how it failed in equilibrium. All right, terminating video. Please feel free to tell me to redo the video. You know what? I'll make it private. Put your comments there. Maybe you guys have the right wording for me that I need, and I'll reword it and do the video again.